Okay, so good morning, everybody. Welcome to the today's special lecture on 2019's Nobel Prize, and it's a pleasure to have Professor Charles Lineweaver with us, and he has graciously agreed to give two back-to-back talks, yesterday's talk and today's talk, and he's from Australian National University. He's the convener of Planetary Science Institute at the Australian National University, and he's also associate professor in the research school of ANU. And of course, he works on in many pioneering field, starting from cosmology, astrobiology, extragalactic astronomy, stellar astronomy, and whatnot, whatever you can think. So especially the Nobel Prize has kind of, I would say, strong connection with him. So in 2006 Nobel Prize in cosmology, CMB anisotropy, he has made significant contribution to that. And also this year's Nobel Prizes, which half goes to cosmology and half planetary science, and he's a black belt in both of them. So without further delay, so to Charles.
Yes, thank you very much. Yes, it is true that I am one of the few scientists who are involved in both of the research here that's being rewarded. I know Jim Peebles pretty well because I did cosmology, and I still do cosmology, but now I do more exoplanet stuff, and as you heard yesterday, I do astrobiology. Now, I should point out that these guys do not know anything about biology. They know about physics. And these guys are the exoplanet experts, and he is the physical cosmologist. And I'm not sure, but he may have been the one who invented the term physical cosmology. It may have just been called cosmology before that. So here's a picture of them. And hello. Here's a picture of them, a real picture rather than a drawing by the Academy. And then you notice they're in different order, so I flipped these thing so they'd be in the same order as that picture, so you can just compare. Hello. All right. Okay. Hello. There we go. All right. So here's what the Academy said: for physical cosmology and an exoplanet orbiting a solar-type star, for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. And when I read that, I said, you know what, they should have said our solar system's place in the cosmos, because when you think of Earth, I think, as an astrobiologist, I think of life. And as I just said, these guys don't talk about life. They're not interested in life. They're real astronomy and physical scientists, not biologists. And so I would have said for the place of our solar system in the universe, because that's what we really have found, especially this exoplanet discovery. And as yesterday, if you have any comments about anything, just call out or question or anything. All right, so notice that Jim Peebles gets 1/2 and these guys get 1/4 each. And that's an interesting detail about the Nobel Prize, that it's always divided. So it's very often divided 1/2, and these two people share the other half. For example, the vice chancellor of my university, Australian National University, is Brian Schmidt, and he and Adam Rees got half the Nobel Prize, and Saul Perlmutter got the other half. And I know both of them very well, because Saul, as a matter of fact, when I was preparing my first talk ever about the results of the DMR instrument on the COBE satellite, Saul was the guy who took me aside and said, he helped me make a good presentation. He said, oh, don't say that, or do say this. And he's a very helpful guy. I should point out that he got the Nobel Prize with Brian and Adam Rees in 2011 for the discovery of the acceleration of the universe. All right. And this is what I get. I Googled this, and I noticed that when I Google things in India, there are more Indian results come up. And so they characterize this discovery as the unknown and an exoplanet. So here's the guy who talks about the unknown, and here are the guys who discovered an exoplanet. And then for the first time, I keep on having to look up this word "lak," and I know it's 400,000 years after the Big Bang. And Jim Peebles, if you was a physical cosmologist, but he's not a quantum cosmologist. He's not a particle physicist. He really is somebody who deals with the results of quantum cosmology. He looks at galaxies and galaxy clusters. As a matter of fact, at Berkeley, I had one of my professors was Mark Davis, and I almost became his PhD student, but he went on sabbatical during the year that I had to choose a PhD supervisor, and that's why I chose George Smoot, because they had just launched this COBE satellite. Anyway, Mark Davis I mentioned because Mark Davis was a PhD student of Jim Peebles at Princeton. So here's Jim Peebles. He's sometimes characterized as having a little head with big feet, and they exaggerated this, and this is a newspaper report, I guess a day ago, and Winnipeg-born physicist. So he's been at Princeton for almost his entire life. I think when he went to graduate school, maybe he even went to, does anybody know whether he did undergraduate at Princeton too? University of Manitoba undergraduate, and then for PhD? Princeton, and then Princeton for postdoc in Princeton with Dickey. All right, so Manitoba-born Jim Peebles, this is a Canadian newspaper, right? Just like, I think in Indian newspapers they said Banerjee for the economics. Well, he was, all right. So Jim Peebles, physical cosmology. It's interesting because it's kind of like Jim Peebles has been at the forefront of many, many, many things, but he's never made a discovery like an exoplanet. So I don't think he's ever had a press release that made it to the front cover of newspapers. But he has been one of the most authoritative figures, maybe the most authoritative figure in physical cosmology. And that's why I call this kind of a Lifetime Achievement Award. And that's kind of interesting for the Nobel Prize because they're not supposed to do that, I guess, a Lifetime Achievement Award. I thought, if they're going to give Lifetime Achievement Award, they should have given one to Stephen Hawking before he passed. Anyway, they gave it to him, and he's a theoretical cosmologist at Princeton University who helped predict and then interpret the cosmic microwave background. Now that is true. He really did help predict it. He was in Dickey's group, and maybe he should have gotten the Nobel Prize in 1978 with Penzias and Wilson, because there the Nobel Prize Committee made the decision, hey, these guys discovered something. They didn't know what they discovered. Dickey comes along and tells them what they discovered, and then Dickey does not get the prize. Now, I should say that Peebles worked very, very closely with Peebles. Peebles worked very, very closely with Dickey at this time. And so maybe Peebles should have gotten the Nobel Prize 50 years ago for his and Dickey's interpretation of the excess noise that Penzias and Wilson had seen. But it's kind of weird that they choose, the observer detected something, and these guys told them what they detected. I mean, if Dickey wasn't around, Penzias and Wilson wouldn't have gotten the Nobel Prize because they didn't know what they discovered. Maybe it would have been discovered, the interpretation, correct interpretation, might have come 10 years later or something. But anyway, it's a kind of...
George Gamow had predicted it.
Well, George Gamow kind of predicted. His students, Alpha and Herman, are the ones who did the hard work to get a temperature for this hot Big Bang that Gamow had promoted. So there again, it's a little bit complicated. There's a book on this as well, if you're interested. A big, rich history behind this. Anyway, now I should point out, interestingly, if you know Peebles' work, he doesn't talk about the CMB. And the reason he doesn't is because it's a microwave. Microwave is the frequency that you have now. But this thing has started out at about 3,000 Kelvin, and that's not microwave, but now it's 3 Kelvin, right? So a factor of 1,000 shifts. So this background, he calls it the cosmic background radiation, to get away from this term microwave, because in a billion years it won't be microwave anymore, and just as you get closer and closer to the surface of less scattering, it also wasn't microwave there. It was hotter and hotter and hotter. It wasn't 3 degrees, it was 3,000. And so that's the kind of, that's the reason that Peebles always refers to it as the CBR. As far as I know, maybe he changed over in the last 10 or 20 years, but his earlier work always said CBR. Now, here it says he really did help predict and interpret the cosmic microwave background. For example, one of the things that I was most interested in with this DMR result was the dipole and the rest frame of the universe, because I was told, hey, special relativity, there is no preferred rest frame. You know, you don't know how fast you're going, it's all relative. But this microwave background provides a rest frame to the universe. And I thought, that's kind of weird. you have a rest frame of the universe defined by the reference frame which does not see a dipole. So if they're surrounded by photons, if I'm going like this, it's hotter there and cooler here, I'm moving. But if I'm standing here and it's hotter there and cooler there, that means I'm moving in that direction. Now this is something I think very profound, because when I talk to quantum cosmologists, they always talk about a false vacuum, and how the false vacuum dumped all the matter into the universe and the photons. But the problem is, if you have just a lambda universe, you do not have a rest frame. So when that lambda energy, the false vacuum energy, was dumped into the universe, that's when this reference frame was created. And I've always found that a really weird paradox of how in the world did this non-reference frame come up with a particular reference frame, and that is the rest frame of the CMB. Isn't that profound, Sam? Anyway, I find that very profound, how quantum cosmologists can talk about a lambda universe, no matter, no photons, and then it dumps the things into the universe, and then you have, all presto changeo, a reference frame, with respect to which we have a velocity. And I wrote the papers from the DMR on the dipole, and it's kind of nice to know what your speed is with respect to the microwave background. Peebles he wrote a wonderful paper about showing that, hey, when you have a velocity with respect to the photons, you maintain the black body nature, but you just go to hotter temperature in front and cooler temperature behind. And he showed about how it's distributed in angular scale too. Pretty complicated. It's a nice, simple, but also very insightful contribution. This was very early. This was like in 1968, soon after Penzias and Wilson's discovery. All right, now here's let me stop this. This is a press release of, I thought I would let Peebles talk for himself here. Anyway, so can I turn this up a little bit, or just get the microphone down here maybe? So let's see if it works.
We're on to wonderful discoveries. Science marches on in many directions. I don't think there is a final theory of anything. It's theories all the way down. Some will go to our children. We're in this for the joy of research, the fascination, the love of science. That's the reward, really. I remember being startled when I was told that you could be paid for doing this. Don't judge yourself by the awards. Judge yourself by how well you've done. And do your best.
All right, that was the tasteful press conference at Princeton University. All right, now here's turtles all the way down. Now, he said in that release, he said theories all the way down. And I thought that was a really weird thing to say. Theories all the way down. And so he's making fun of this idea. You know, there's a story about a woman and a man, and a woman talking to a cosmologist. And she says, I think the Earth rests on the turtle's back. And he said, well, what does what does the turtle rest on? And she says, don't try to fool me. It's turtles all the way down. And so that, I'm not sure, is that a proverb of some culture? I'm not sure where that comes from, but turtles all the way down is something that's well known. And so here's a picture of turtles all the way down. And the idea of having theories all the way down kind of is jarring, because most physicists think, well, there's objective reality down there, and we make those observations of objective reality, and then we create a theory to explain that. And the idea of having theories all the way down rather than observations is something a little bit weird. Okay. Now, Eddington said, it is also a good rule not to put over much confidence in the observational results that are put forward until they are confirmed by theory. So this is something that I have, the head of the Research School of Astronomy and Astrophysics, where I am, my boss is Matthew Collis, and sometimes we debate about this. And I agree with Eddington that every observation has to be confirmed by theory, just because you theorists make so many problems, make so many mistakes, so many systematic errors crop in. And so, but if you have a theory that suggests, oh, that makes a lot of sense because of blah, 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 then you get your observations confirmed. But if your theory says, there's no way in hell that that's true, that can't be true, it must be a mistake, well, then your observations have not been confirmed by theory. It's just part of the give and take that goes back and forth between theory and observations. That's so healthy a thing. Peebles is definitely on the theory side, and he didn't say observations all the way down, he said theories all the way down. So he probably would agree with this statement, that every observational result, you shouldn't believe in it too much until it's confirmed by theory. Maybe to take a poll. Anybody agree with that? Who agrees with that? Oh, Sam, you want to comment?
No, I just want to
Say it loudly, please.
perhaps it's a dig at the people who say there's a final theory.
Yes, there's definitely a dig at the people who say it's a final theory, but if there's a final theory, isn't that means there's no end to the theories, I guess. No final theory. Well, then there's no all the way down. Just keeps on going. Okay, well. No final understanding. All right. Well, anyway, that I think what about Hawking? Did Hawking believe that? Would he agree with that? Or did Hawking think there was a final theory? I know that Weinberg wrote a book called The Final Theory, right? Anyway, this is a hot topic of theoretical physics, whether there is or is not a final theory of everything. Stay tuned. Now, I want to say yesterday I showed this plot, and I put an integral sign here, and what I did a mistake here, and it should have been just this. But I wanted to point it out for the students, again, to emphasize the point of how important this is to get from here to there. And I'm sorry I made this mistake. Sam, I talked about this yesterday, and he thought it was a convolution, but I think it wasn't a convolution that I wanted. I just wanted a simple multiplication. I was being too fancy in front of a very sophisticated mathematical audience. All right. So, now, if you want to know about the history, because this is a Lifetime Achievement Award for Jim Peebles, there's a lot of history involved. And if you want to look at pre-CMB cosmology, you can do no better than to look at these two books here. Now, I have not read these books, but every time I read, boy, if you want to know something really weird, look at Cosmology before the detection of the CMB by Penzias and Wilson. So has anybody read these books? Does anybody possess these books? Okay, you're not interested in the history of science, okay? If you are, have a look at these two books. I recommend it. I'm going to get this one because it's the cosmology textbook, a standard, just before the detection of the CMB and the hot Big Bang. All right. So also, if you're interested in the history of science, Helga Craig is a very respectable, she writes very well about, this is the Cosmology and Controversy. Here she's talking about 1920 to 1970 about. And here she's talking about grand theories and failed revolutions in physics and cosmology, the multiverse model, for example. Okay. Now, this, in 1965, remember I told you that Dickey told Penzias and Wilson what they had discovered? Well, this is Dickey, and here's 1965, includes this diagram. Peebles, for 20, 30 years, has published diagrams like this. And here's the radius of the universe in arbitrary units. Here's now. Here's the 10 to the minus, when the universe was 10 billion times smaller. And here's units in seconds. So here's 1 second after the Big Bang. Here's the temperature going down. And the temperature now is somewhere around 3 or 10 or something. But actually, they tried to probably align. Since this paper was published in the same issue as the Penzias and Wilson paper, they probably drew this so it is exactly about, well, 3 or 4 Kelvin. And this is the density of the universe for these two plots in radiation and in matter. So they really, Peebles is the person with Dickey who started to talk about cosmology in terms of the transition from radiation to matter, when plasma recombines, when helium was formed. It is true that Gamow talked about this earlier, but Peebles and Dickey at Princeton are the ones who really developed this. And talk about matter and radiation equilibrium right here, Z equality here. So that paper that they talked about well, wait, here's the Penzias and Wilson standing next to the Holmdel antenna, and that's where they had the famous pigeon poo that they looked and tried to remove because they really thought this was a systematic error, there's something wrong, and they tried and tried and tried to understand this noise, and they couldn't. And then the story goes that Jim Peebles, who was he was a young postdoc working with Dickey, gave a talk about his work, at Johns Hopkins. In the audience was a guy named Bernie Burke. Bernie Burke is a very affable, very friendly, and outgoing physicist at MIT. Bernie Burke was then riding on an airplane next to either Penzias or Wilson, I don't know which one, and he said, oh, by the way, they started talking about science, and Penzias started talking about this unknown noise. Burke says, well, you know what I just heard from Peebles, I think that maybe you've seen something, so you should talk to each other. So Bernie Burke was the affable old uncle who put these two in contact with each other. So then Dickey visited Penzias and Wilson, and he said, I think you scooped us. And actually it was a telephone call where he says, I think we've been scooped, guys. And then they went over and visited as a group to see their antenna. And that's when Dickey and his group told Penzias and Wilson what they had found. Now, Peebles, now this is the article. Right here is the end of the article by Dickey, Peebles, Roland Wilson in May 1965. And the next article in the APJ is a measurement of excess antenna temperature, 3.5 Kelvin. Then they say, a possible explanation for the observed excess noise temperature is the one given by Dickey, Peebles, Roll, and Wilkinson in a companion letter in this issue, which is right above it, the same one. So these guys really, maybe they deserve a Nobel Prize 50 years ago. All right. I'm having a little problem with this. Oh, there it goes. All right, so now yesterday I showed George Smoot and John Mather getting the 2011 Nobel Prize for George, our detection of anisotropy in the microwave background, and I showed that nice map with the hot spots and cool spots. And then I put up a map of John Mather's discovery, and that was just a plain map. Well, this is really the parameter space in which you can understand what Mather and the PHI-RES instrument on the Kobe satellite did. And that was, they discovered that right around here, it was as perfect a black body as you could measure. Matter of fact, it's the gray. See the gray there? The gray from here to here? That's the PHI-RES range. And the Penzias and Wilson is right about here. I think it might be one of these dots. I thought it would be these, but it was at 4 gigahertz, right? Is everybody 4 gigahertz? So 4 gigahertz is right. This is 1 to 2, 3, 4. So right about here. Anyway, we have a black body. We have a black body with fluctuations around that temperature at the level of a few times 10 to the minus 5. So if you get a cue ball or a pool ball and look at it, it's really smooth, that cue ball is not as smooth as this radiation. So when you see those anisotropies, remember those have been exaggerated enormously by a factor of about 100,000 so you can see them. Although in reality, it's almost a perfect black body. All right, so Peebles wrote a textbook called Physical Cosmology in 1971. He then wrote The Large-Scale Structure of the Universe in 1980. And if you read these books, you will see lots and lots of stuff. The first one, 1971, is a larger fraction is about the cosmic microwave background. This one is about structure in galaxies. And here they were just starting to make these maps of the local universe, and they were finding the Great Wall, and they were finding filaments. And Peebles was somebody in my mind who knew how to analyze 1-point, 2-point, 3-point correlation functions, and it got very arbitrarily sophisticated in mathematics. But essentially, he was working on 2- and 3-point correlation functions of the local universe because that's the only place we had maps of. And he was one of the persons behind getting those maps bigger and bigger and bigger. And now we can say, for example, that the galaxies are not randomly distributed. You know, they look kind of random when you look up at them, but when you plot them in three-dimensional space, you see walls and filaments. And those are the structures, the large-scale structure that Peebles is really an expert in. So he's not an astroparticle physicist, he's not a quantum cosmologist, and he's not somebody who's a local observer. He's a theorist of the galactic distribution, I think is another way to say it. At least that's what he started out as. So if you're interested in the history of the CMB, this is a book that Peebles wrote with Lyman Page and Bruce Partridge, 2009, Cambridge University Press, and this is a puzzle of the map that had just been made by the WMAP satellite, to which Princeton University contributed quite a bit. They were one of the leading institutes behind the WMAP detections of anisotropies. So this is Peebles. This was in 1990, I think. Peebles' book on physical cosmology. Does anybody have this book? Who's read this book or looked at it? Okay, we have a few people here. Okay, maybe a third of the audience. So I wanted to say that this was written, and I kind of grew up in cosmology reading this book. But then Peacock came along, and I think in 1999 he wrote another one. This is called The Principles of Physical Cosmology. Peacock's book is called Physical Cosmology. And then more recently, there's been a really good book I haven't read by Andrew Little, who's more of an inflationary cosmologist. But anyway, Peebles has written quite a few books. And I just wanted to show you the progress that has been made in anisotropy detection since our discovery in 1992, WMAP in 2009, and then Planck a few years later. And you can see that the angular resolution gets better and better as time goes on. I'm not sure if there's another satellite in the works to do another full sky, but remember, this is full sky. This is everywhere you look. Now, this particular map that's showing here includes the galactic foreground. And the DMR had 3 frequencies. I think WMAP had 5, and then maybe Planck had something like 7. In other words, the more frequencies you have, the more effectively you can remove this foreground contamination, which is our galactic plane. And remember, when you're looking at this, the way you should interpret these maps is you take that map, just wrap it around your head, so every direction you see something, and that's what in other words, it's all 4 pi steradians. And isn't that great? I call this particular thing, see that it's kind of dark here, this is a cool spot, cool spot, cool spot. You can see and I call this the Smoot Pit. These things do not have names yet, by the way. You notice that when you have a satellite that goes around a planet for the first time. For example, the Russian satellite took the first picture of the backside of the moon, so all the big structures on the backside of the moon have Russian names to them, right? But for some reason, the microwave background community has not given names to these structures. And it's kind of weird because this might be the largest structure in the universe, right here. And anyway, I call it the Smoot Pit to kind of tease George about this. They did a better job of removing. We did also remove a galaxy, but it had too much noise in it, and it was not a good map. And then they had the frequency coverage to remove the galaxy very well, and these guys had even better frequency coverage to remove the galaxy, so they can trust that there's probably a little bit of galactic plane contamination, but not much. Any questions?
Could you explain the significance of the colors?
The significance of the colors. Okay. Well, this is not in the visible, so there are no colors, for number one. It's kind of like a radio map. You see those maps of radio, and they colorize it sometimes. So this is a combination of 53 and 90 gigahertz maps. And what you do is you have high intensity and low intensity, and then you assign arbitrarily a color. So these are false color maps. But the hot is red, and the cool is dark. So this is a cool spot. This is a hot spot. This is a hot spot. Now this is hot from the galaxy, but this is a hot spot. This is a cool spot. And the cool spots correspond to underdensities. And so you have photons well, wait a minute, no, I got that wrong. This is a Sachs-Wolf effect. If you have an overdensity of matter, sometimes you have more matter here, less matter here, more matter here. Remember, these are density fluctuations in the early universe that were imprinted on the universe by quantum fluctuations. So you don't have a perfectly smooth universe. You have a universe that has imprinted on it quantum fluctuations. So then you have overdensities and underdensities, and so when you have an overdensity, you have a potential well. When you have hot, a little bit hotter at the bottom of that potential well, because you could think these are called adiabatic fluctuations. You have photons coming out of those gravitational wells. As they come out, they get cooler because they're losing energy. For the same reason that when I shine my laser up here, it gets a longer and longer wavelength because of the gravitational field it's going out of. So the cool spots here are photons that are trying to get out and are leaving a potential well and getting colder as they do. The bright spots are potential hills. So they're falling down. They're under densities, so they're falling down a potential well. They're not in a potential well. They're falling down a potential hill, and therefore they're getting hot. What I just said is true in the Sachs-Wolf regime, which is up and, well, it's a large scale. It's the scale at which this map was made. These maps, the large scale fluctuations is the same thing, but as you get to smaller scale, then you have compressions going on, because then you become causal. You have spots which can change because of motion. At large scale, you have super horizon fluctuations. And those super horizon fluctuations are what made Stephen Hawking say, hey, this is the greatest discovery of the century, if not of all time, because we had seen things which could not have been caused by processes other than the quantum imprinting on the universe. And so when you so this is cold, this is cold, and that's hot. So they chose blue is cold and red is hot. And then the same thing here, that's cold, and now this is hot. So these are the PIs who get to choose the color scheme. And it's kind of confusing because, you know, for a star, red is cool and blue is hot, right? So it's just the opposite for a good physicist who takes his black body temperatures seriously. This is the wrong way around. But George chose these because, you know, when you go into a shower, the hot is red and the cold is blue, and so that's why he chose it, really. Seriously, that's why he chose that color scheme. All right. Yeah, yes? Well, if it was a billion years ago, that's a redshift of what, 0.4 or something? So you'd be hotter by a fact, maybe it would be, instead of 2.7 Kelvin, I'm guessing, anybody can do this math in their head? And it would be a little bit warmer, I'm guessing 5 Kelvin. You go even higher redshift, it's 10 Kelvin.
That I understand. What I'm saying is the fluctuations,
Yes.
will they still look the same?
Well, because they're over densities, well, let me go back. Hello. All right, so you're saying, so let's put ourselves in a time machine, get our instruments out there, and go back and look at it a billion years ago, a billion years ago, a billion years ago. And I think the answer to your question is, on the large scale, yes, more or less. The reason I say more or less is because if you go back in time, your surface of last scattering, you're closer to it because it's receding at the speed of light. So essentially, you're looking at a surface of last scattering that's closer, and therefore, the structures that you see here would be bigger. Because they, on super horizon scales, they do not evolve in time. On small scales, they do, they're small enough to evolve, and therefore, they would be getting bigger in size, okay, as time progresses. Somebody should make a simulation of this. I think maybe there is one, but I haven't looked at it carefully, of the microwave background as a function of time. If you started out losing these instruments right at recombination, what would you see? I should say that artists often portray the Big Bang as a spot, and they go boom, like this. That the Big Bang was not a bang in space. No cosmologist could say, the Big Bang happened over here. The Big Bang happened everywhere. The Big Bang happened in this room. And for an artist that kind of blows the mind of most artists, because they want to put it at a spot and then they have it like a bang. They want to put a firecracker. And that just doesn't work. It's not appropriate. And yet it continues to be propagated by almost everybody, simply because what's the alternative? The alternative is to say, okay, here's a spot of the universe. It's hot, and then it gets bigger and colder. And you have to recognize this is not the universe. It's a spot, an arbitrary excerpt from a small part, rather than the center of the universe being where the spot is. Any other questions? Yeah.
So what level galactic background contribution has been removed in these two?
What level of background radiation has been removed? Well, that level. And so you can see it's a very prominent feature. The same prominent feature is here and here, but they had to remove it. And they're able to remove it because, as I said, they had more frequency coverage. Like we only had 53, 53 and 90, 3 frequencies. With 3 frequencies, it's hard to, now, that background is synchrotron and free-free. So that's the main contribution in this part of the spectrum. Around 50 gigahertz, that's the main contribution. You have free emission from the galaxy and synchrotron emission. At lower frequencies, synchrotron dominates. They have different frequencies, and so if you have, you're removing 2 things, 2 slopes that you know pretty well with 3 measurements, and that's not that easy. But if you have 5, it becomes much easier. If you have 7 or 9, it's much, much easier. And then you can even do it as a function of where you are in. Instead of removing it from the whole galaxy, you say, hey, I'm going to remove free-free and synchrotron from that spot, and that spot, and that spot, because I have my 5 frequencies or 7 frequencies in that spot, and in that spot, and that spot. That enables you to remove. They've assumed, well, you can measure the spectral index, and you assume it, and then you measure it, and assume it, and measure it. It has been measured before by other measurements, and it's pretty good. It's not perfect subtraction, but it's pretty good, and down here it's much better because of the frequency coverage. Any other questions? Okay. All right, so that was Peebles. So I'll stop talking about Peebles. I've talked to him, I've seen him at about 10 conferences and talked to him for 5 or 10 minutes. Usually my questions about cosmology to him were about inflation, and he wasn't an expert in inflation, but he was very skeptical about it. I should say that Princeton, although he's kind of getting credit here for CDM and lambda CDM, they were kind of on the slow end of recognizing the data that backed up these new models. CDM and, I mean, not too far behind, but I remember in 1997 when I first went to Australia, on my way I went to an IAU in Tokyo. And there I talked to Ostreicher, and Ostreicher was still saying, you know what, the universe looks like it's open because, the mega matter is 0.3 or so, and that's it. And I had just presented results from the combination of CMB measurements saying that the best fit suggested that there was a lambda, and but they ignored that because they weren't doing it. All right, Didier and Michel Mayor. Now, these guys are Swiss. He's now working at the University of Cambridge. He's an emeritus professor at the University of Geneva, I think. And so they say the most tantalizing goal of the field, set in motion by Mayor and Queloz, is to find planets that resemble Earth and to detect biosignatures. That's what I talked about yesterday. These guys, Didier is starting to get active in that field. Researchers are already probing the atmospheres of individual worlds using the Hubble Space Telescope and other tools. Next generation instruments, particularly the James Webb Space Telescope and the Wide Field Infrared Survey Telescope, will aid in that effort. So these guys are getting credit for making that first discovery of a planet around a main sequence star. So I should point out that when I was asked by the press about this Nobel Prize, I said, if they gave the Nobel Prize for exoplanets and they could give it to 4 people, they should have given it to these 2 plus Mayor and Queloz. Why? Because I think I told you the story that Marcy and Butler, there's Marcy over here and Butler over here, were doing the same thing as Mayor and Queloz were doing. These guys had worked, their program started earlier. They had more data at the time, but as I said, they thought, well, just going to have to wait before we analyze it. And so Paul Butler didn't analyze it, and if he had, he would have beaten Mayor and Queloz to the discovery. So it's too bad for these guys. But they did find the first planetary system. So they found a star with not only 1 planet, but 2 planets around it. So they get the credit for finding the first planetary system. All right, now, I knew the name Mayor. I've since, Michel, I've met a couple of times, but many of you may know this paper from 1991, Multiplicity Among Solar-Type Stars in the Solar Neighborhood. So what they had was a spectrograph, and they measured they had looked at binary stars, and they measured one star going around another. And so what do you get? You get radial velocity curves. So this curve here, for example, doesn't that look suspiciously like the detection plot of 51 Peg? It's exactly the same thing, except for the y-axis here, it's in kilometers per second rather than meters per second. So Mayor essentially was doing this, you know, when you see it, this is a perfect sine curve. So that's when you get like this. But sometimes you get high eccentricities in binary stars, and that's what these stars, there you can see it's not very much sine-like, and so therefore it has an eccentricity. Here's a really high eccentricity, maybe, I don't know, 0.6 or something. Maybe this is 0.2, and this is probably an eccentricity of close to 0. So he was very familiar with fitting these types of data to curves to figure out what the masses and the periods of these stars were around each other. So he was doing this with stellar companions, and this is a very famous paper, and here's the log p distribution. This is the number of pairs, and this is the periods. And so he got this distribution. I should point out that this is the observed distribution, not the true one, and now there's a couple of better ones that go, and they're more in this region here because they, or no, I guess it'll be more out here because you can look longer to find these. Anyway, I just wanted to show how similar what Mayor was doing. This was a few years, about 4 years earlier, and then he said, you know what, I need a more powerful, this is Correvel, the spectrograph, and then he said, I need a more powerful one. He's living in Switzerland, he's got lots of money, and so he had the money to build a more sensitive spectrograph. That's what's called LOD, and with LOD, he went down from 50 kilometers a second to 50 meters per second. Right? And so that's a factor of 1,000, and so good for him. And then he had a PhD student named Didier Queloz who came on board, and they worked together, and Michel Mayor told him how to do all these fits, and then Michel Mayor went on sabbatical. And then Didier, while Michel was on sabbatical, Didier found this thing. He said, hey, and he knew he thought, oh, this has got to be a mistake. But then he used the same instrument on another star, didn't see anything. The systematic error was not in where he looked at other stars. He looked back at this one, he found the same pattern. We found something. He emailed to Michel, who was on sabbatical, and Michel said, hey, we'll see. Wait till I get back. Don't tell anybody. And then they published the paper. Okay, so here's that paper. That essentially, this is a one-paper Nobel Prize. And we talked about it yesterday, but there it is. They discovered this thing about a year, maybe even a year and a half earlier, but they wanted to make sure. And here is that, here is this, see, meters per second, 50, and the other one was kilometers per second, 50. So it's a factor of 1,000 improvement in the sensitivity of the spectrograph. And again, remember, we're looking at the host star. You're not seeing the planet at all. All you are seeing are the absorption lines in the spectrum of this host star going backwards and forwards as it goes 50 meters per second this way, 50 meters per second this way. Now 50 meters per second is pretty far. It's like going here in a third of a second in this room. So it's a sizable velocity. And right now we've improved that maybe by a factor of 100 in spectrographs now. In any case, red absorption lines going back and forth. Is everybody clear about that detection rate? Yes? Two different instruments. One was the Correvel was the spectrograph they used for the binary Duquesnoy and Mayor 1991 paper, and this is called LOD, which is a... For the what? Two different spectrographs, yes. Two different
spectrographs of the same system?
No, it's different system. These are different systems. This is one particular system. Yeah, I shouldn't pretend that all binary stars give you 50 kilometers a second. No, that's not. So I just was showing that as an example. Okay. All right, so I wanted to show you this plot again because on it, I didn't say, because Didier and Queloz got this prize for finding this planet, but also because they launched this incredible new field of exoplanet detections, which is ongoing today and probably will dominate astronomy for a long time to come. And for example, when somebody comes up with a new telescope concept, they often have to have a science case based in part on detecting exoplanets or detecting life. And I've noticed that in the last 10 years that everybody says, hey, we're going to find life. And it's not an easy thing, but it's sometimes used as a token, but a lot of instruments are specifically designed to find exoplanets. And I did want to talk about the other example. So the blue here is the radial velocity. That's the technique that Didier Queloz and Marcy and Butler were using. Then there's a transit. That's when you look at a star and then it gets a little bit dimmer because a planet passes right in front of it. Then you have Kepler, which is also a transit. Then you have the solar system planets. Then you have direct imaging. Now, direct imaging is something, if there's a star there, you can only detect direct image. Look at where they are. They're way up here, so they're very large periods, so they're very distant from their host stars. And now here's the trick. They have to be giant, and they have to be young. And the reason they have to be young is because only when a giant Jupiter-like planet is collapsing in the first, let's say, 100 million, maybe 200 million years, is it shining with the accretion energy from its collapse. After half a billion, after a billion years, that energy is all gone, it's dim, chances of seeing it go way, way down. And so when you see direct imaging of planets, you can say they have to be far away, and they have to be young, hot Jupiters. You're never going to detect an Earth-like planet with that technique. Although people are trying. Well, then you have microlensing technique. That is when you have a background source, and then something passes in front of that background source, it causes a lensing event, right? But if that something here has a planet around it, it causes it gets brighter and brighter and brighter, and then boop, it gets a little blip in it. That little blip is the planet adding its contribution to the gravitational lensing from the star that's passing directly in front of a background star. That's what microlensing is. That's kind of cool. It's interesting. But it only happens once. Once it does that, it's very unlikely that that same object will pass in front of another star to give you another microlensing event and then to verify what you've seen. So that's one of the weaknesses of the microlensing technique. And then there's pulsar timing, which is the same thing as radial velocity, but instead of around a main sequence star, you're going around a pulsar. And the bleeps, you have the bleep, you go bleep, 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 bleep. And then if the pulsar is going like this in reflex motion, then it gets faster and slower. The beeps get higher frequency and then lower frequency. The same thing. Matter of fact, it's even more accurate, apparently, than the RV technique from the LED spectrograph, because, look at this, the lowest mass star is detected by pulsar timing. So for some reason that I don't know enough about, pulsar timing has the most precision to detect those frequency changes in neutron star hosts. Any questions about this? Yeah?
For the microlensing, there must be some also, not just the mass of the planet. If it's too little, also it won't be shooting.
That's right. That's right. That's right. The bigger the planet, the more, well, the star that's passing in front is doing most of the lensing, right? And it's making the background object get brighter and brighter and brighter and brighter. And then it gets dimmer and dimmer. But as it's going up or as it's going down, sometimes the planet gets closer to the direct, you know that.
No, what I'm really asking is that do I know what is the sensitivity of this for the ratio?
Yes. Yes. Now, let me try to remember if you ask the question, where on this plot is microlensing the most sensitive? If that's your question, then the answer is right here. Now, see the green? There's green, 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 green. So it's right about here. That's where it's sensitive. And then it goes like this. And so you can see that's where the greens are. See, green, 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 green. And so that's where it's the most sensitive.
So there should be a range in masses.
Yes, but it's easier to detect more massive ones, right?
Exactly. That's what I thought. But at the other hand, there seems to be
a sweet spot in period, and that sweet spot is right around Jupiter. See that? That's why the green crosses are in that region. You can do the same thing for every one of these techniques. Where's the sweet spot? Where's it most sensitive? And that you need to know because you're trying to interpret where are the planets really? These are the ones you've detected, but where are they really? You want the the mother distribution, the underlying truth, and that's why you need the sensitivity understanding of your instrument, so in both time and in signal to noise. Yeah? Excuse me? The red points, okay. So now you're asking, you know it's a transit measurement. So therefore you're finding what the transits do is they see how much light is dimmed from a particular star. So in order to get that, the planet is passing in front, right? So that's making the dimming. And so you have to have an estimate of the size of that star. It's very important. You have to convert the luminosity to a size of that star, and so that's the first model you have to do. And then you see how much it's dimmed, and that tells you the ratio of the size of the planet to the size of the star. Right? So that gives size. And then you say, well, for something that's big, how much is the mass we think? You have to convert radius to mass using formula, which we now know better because we have a couple of hundred, maybe 400 planets in which we have measurements of both radial velocity and eclipsing transits. And that tells you approximately where the most of the points lie. That's a functional form that you can then, if you have only R, boop, you can find M like that. So that's what's used to put the transits on this plot. I don't think a factor of a few off, maybe 50%. I would not a factor of 2 or 3, but rather 0.5 or so. I should also mention that you could also ask the same question about the radial velocity points. You're getting M sine I, you're not getting M, and yet I've plotted M here, right? And so what we've done there is just taken the average of what a sine I is based on all of the arbitrary inclinations and then used that value as a standard. So for the RV ones, some of these are minimal masses. Yes, you have to go through some modeling to make this plot. The overall distribution is? That's what we're trying to present. Well, let's take, for example, let's suppose that object right there, right? So the M sine I gives you a minimum mass. That minimum mass is probably somewhere around here, and then the distribution goes arbitrarily high because you could get arbitrarily flat. But the probability of being exactly face on is not that large, and so, anyway, that's the kind of the calculation, and you're right that this is a statistical distribution that shows the statistical truth, not the individual ones. Except for ones that we're now getting, we have about 400 of the 4,000, so about 10% now have both RV and transits. And I should say one of the weak points of Kepler is they were looking at, remember, very far away, 200,000 stars, many of which were too faint to get RV follow-ups. But the TESS ones, they are brighter, and there the RV follow-ups will be easier to do, and therefore almost every TESS detection will have an RV follow-up and get rid of some of the ambiguities that we've just discussed.
So basically, once test comes, we get more data from that. This will be kind of covered.
When TESS comes on, now TESS is discovering something like, 50 planets a month or so. But as I said yesterday, here's 10 days and here's 100 days. TESS's planets will almost always be less than about 20 days. And there will be TESS will probably fill in this region right here. That's where it's most sensitive. It can't do anything about this. It is even less sensitive than Kepler to real Earths with 300-day periods. With one exception, and that is because it's going full sky, going like this, the ecliptic pole, all these stripes overlap, and so there you're getting observations that last as long as TESS lasts. Well, I should say half as long as TESS, because they do the northern hemisphere and then you get here, and then they do the southern hemisphere, then you get there. And so the northern ecliptic pole and the southern ecliptic pole has been looked at for half of the TESS mission. A spot, I'm guessing about maybe that big, something like that. So there will be some there, so there will be some TESS points here. On the other hand, TESS stars are bright enough to follow up. RV can do it, and then RV can look arbitrarily long. Then, matter of fact, they're following up with test things right now. So they can look a month, they can look 6 months, they can look a year, they can look 2 years, and then find, and because it's online, the RV gives you the mass without the sin I problem. And so you can put, eventually, from one that was detected here, we can put a whole string. Notice that I haven't put planetary systems on here. I haven't connected the dots from planets that are in the same system. I could do that, but it would make a lot of messy things. Very messy. Any other questions? All right. So here's the, yesterday I talked about the Hertzsprung-Russell diagram, and there was some concern about the stars down here. Remember, these are the host stars that TESS will be looking at, because the habitable zone that we're interested in has an orbital period of 5 or 10 or 15 days around these very dim stars. And if you take the plot I showed you, we looked at for a long time, and say, you know what, I'm going to take the period, and I know the brightness of the star, and I use Kepler's third law to turn period with the mass of the host into a distance from the host star. Then I assume an albedo of something like 0.3, and then I can convert period into effective temperature, and that's what this plot is. Here's instead of having period, you have effective temperature, and here is mass, this time in Earth masses, and here is the habitable zone. Here's where the Earth is, for example. There's Mars. And if a planet is up here, it's really massive, it might have a moon, kind of like Titan, that has an atmosphere. And if you have a moon and an atmosphere that's close enough to be in the habitable zone, then you can have a habitable moon. And that, I think, was what the subject of Avatar was. Right? There was a hot Saturn or something, and then that hot Saturn was in the Saturn was in a habitable zone, and it had a rocky moon orbiting it, and that was the habited thing. So anyway, so this is done. We did this in 2012 in our paper, in a review article in the Reviews of Earth and Planetary Science. And it's pretty much the same thing, but as I said, the period has been converted to effective temperature. And you can see that there's not much here. And you go up to 2 Earth masses or 3 Earth masses, then you start to get something in the habitable zone. And what we're looking for are planets here, here, here. And I'm sure there are lots and lots that are there. All right. Oh, boy. Oh, boy. So the circumstellar habitable zone is something like this. These are life forms that like to be at 37 Kelvin, 37 Celsius. And like you and I. And when it's cold outside, they get around a certain distance from a fire, and this person wants to warm up their hands, and so they're a little bit warmer, closer to the central star. And so it's kind of like a habitable zone around this fire. That's the same thing as what's called a habitable zone, circumstellar habitable zone. You have it's too hot here, it's just right here, and it's too cold here. We did a paper in 2015 in which we did some extrapolation of the statistics, and we found that an average number of planets in the habitable zone is 2 plus or minus 1. And you can look at that paper here if you're interested. So just to show you the sizes of circumstellar habitable zones and how different they are, if your host star has a mass of 2 solar masses, you have this size habitable zone. It's farther away from the central star, which is right here, and it's very wide. Here's Alpha Centaurus A and B. The Sun is somewhere in the middle here. This is a little bit more massive, 10% more massive than the Sun, 10% less massive. And Proxima Centauri, for those of you in the back, there's a spot right there. Can you see that? Right there? That's the size of the habitable zone around Proxima Centauri, and that's where we found the closest habitable planet. And for the next 10 years, you will see in the newspapers habitable zone planets in habitable zones that are that big because of the constraints of the TESS satellite only looking for a month and then moving on. And so you're not sensitive to habitable zone planets around sun-like stars, only around M dwarfs. Now I wanted to show one problem with that type of habitable zone. Okay, so there's a stellar mass dependence of the habitable zone. Here's the radius relative to Earth's orbit. Here's the Earth. And here's the mass of the star, and so the habitable zone kind of gets further and further away if you get more and more massive stars. Now, here's what I was talking about yesterday about the vertical nature of the pre-main sequence tracks on the Hertzsprung-Russell diagram, that it might be a killer for the volatiles that presumably might be enabling life on currently in the habitable zone planets around M dwarfs. And so here's the sun right here, and it takes about 40 or 50 million years for this to go jit. So this is 10 to the 5 years, 10 to the 6, and then onto the main sequence, and that's where we are now. And the sun is slowly getting more luminous because it's burning that hydrogen in the central core. But look at the tracks as you get lower and lower. They're very vertical here. And it takes, this is 100 million years, but I think it takes about a billion years to get from here to here. I've tried to investigate this a little bit more carefully, but there's some uncertainty in the theoretical modeling of these tracks. Anyway, so here's why the main reason why life on Earth will probably go extinct in about a billion years. These are post-main sequence tracks. So here's the sun, and what is happening to the sun? It's getting brighter and brighter and brighter. What is that doing? It's making the habitable zone move further away. So I think so here's the age of the sun in billions of years, and here's where we are today. Here's distance from the sun, and this is supposed to represent the conservative and the optimistic estimate of a habitable zone. And notice it's going up, 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 up. It's getting further away. So the Earth is becoming less habitable, and Mars is becoming more habitable. Why? Because the sun is getting brighter. So now Mars, it looks like it used to have water on its surface. Now the pressure on Mars in the atmosphere is below the triple point of water, so you cannot have water on the surface of Mars. But if you heat it up, and it's going to get hotter, a lot of the water that's in the ice now will come out, go into the atmosphere. Maybe there'll be enough to raise the pressure on Mars above the triple point of water, and then you will have water on the surface of Mars again. And then the Earth will get too hot, too overpopulated, too polluted, and we'll all move to Mars with Elon Musk's giant rocket. But there have been about half a dozen papers written on the future of Earth and when it will become uninhabited, and the bottom line is something like a billion years from now, plus or minus half a billion. Big error bar, but that's the extent to which the people who have modeled this increase in luminosity and what happens to our atmosphere, how we lose water and it gets hot. That's what's going to happen to us. So prepare for that. And thank you very much. Thank you very much. And I don't know, are there questions now? Or okay, any questions about the death of the planet Earth in a billion years? Yes, sir.
I think if this prize had been given 5 years ago, I think Vera Rubin might have had a strong shot, and Marcy would not have been toxic.
Yeah, that's right, that's right. So that's right, Vera Rubin would contribute a lot in her rotation curves to find, hey, that's evidence for dark matter. But how about Zwicky in 1936? He was the first one to come up. Those clusters should not be held together. Those galaxies are zooming around at too high a velocity. There's something wrong. So, I would have thought Zwicky. But the list of characters, science is always like that. Somebody has some evidence. My evidence supports yours, and it's a different kind of but wait a minute, that theory is wrong. And it just goes back and forth like that. And I'm glad I'm not on these committees trying to choose, because almost everything is a group effort. So many good people. And I'm thinking of the Austrian writer who just got the Nobel Prize in Literature. It was very controversial because apparently his poetry is very good, but his politics are in support of Milosevic, and so it's a big controversy. Thankfully, in physics, there's not that many politics except for maybe this Marcy case, so I think if they had given the prize to 4 people, they should have given it to Mayor and Killows and Marcy and Butler, because these 2 groups really, in the first 5 years, they were the only game in town, and it was all RV, and they had planned it years ahead of time, maybe 5 years or so. They've been working very hard, and so that would have been fair, I think, except for the sexual harassment thing that Jeff Marcy had to resign his position at Berkeley in 2015. Yeah?
Coming to the 3D background, there was a guy called
McKellar, yes.
A Canadian guy who had detected it in the temperature of molecules or something.
CN, he detected, so if you look at molecules, you asked the question about what would you see if you went back in time. Well, if you look at things that are at redshift, higher redshift, 0.5 or 1, you're looking when the CMB was a higher temperature. So he's referring to this Canadian guy who was looking at, I think, CN molecules, and they have excitation states. Now, the excitation states are due to some background. And he looked at the excitation rates and he figured out that they were being excited by radiation at something like, I don't know, 6 or 7, maybe even, I think it's 10 or 12 Kelvin. Because he was looking at a redshift of 10 or, at which the microwave background was at 10 or 12 Kelvin. So it was exciting molecules into higher states. And he detected this, and he didn't really interpret it in terms of general background cosmology, George Gamow type of thing. I guess he thought, have you read these papers? I think he thought that maybe there was a local field from stars of some kind that was raising the temperature to that. And so he didn't make the conclusion. He didn't have a Dickey to tell him what he was seeing, I think, is the accurate way to describe that scenario. Any other questions? Sometimes we say students have to ask a question. It's Australia. Sometimes the people in the front ask a question. Then the students, I don't know, they're not confident, but students should definitely ask some questions. So please, student, ask me a question. Some student back there in the safe seats. Hello, students. That's part of your responsibility as a student to ask questions. Yes? Wait, a student? Anyway, go ahead, ask her.
So I have a question about the intensity of the sun and the existence of life on Earth.
Yes.
With the increment of time. So you said the existence of life with increment of time. So existence of life in the future would be less prominent.
All life will die.
Yes. So what do you think about the issues related to global warming and the steps taken towards that?
Oh, we're getting there sooner. Well, the global warming is due to CO2 increasing in the atmosphere, right? So that's something that you can lower. Matter of fact, the history of CO2 in the atmosphere is one of getting lower and lower and lower. And that billion-year time scale of reducing CO2 is sometimes interpreted as Gaia, the biosphere, trying to maintain the temperature cooler, because as the sun gets hotter, you want to decrease the CO2 so you maintain a good temperature. But now the sun is getting hotter, and the CO2 is getting higher. So those are two things that are having a positive feedback. And same thing with melting ice, right? Ice has a high albedo, and then when you get rid of ice, ocean has a low albedo. So you get hotter, you melt the snow, and then you get a lower albedo, and then you get more energy hitting the Earth, and then it melts more snow. So these are positive feedbacks, and that's why they're so hard to predict. These IPCC reports have a difficult time because they have to figure out a nonlinear process that's going on between the CO2. The sun getting warmer is something that's very long scale compared to anything that the IPCC reporting is talking about. So I mentioned billion years. They're talking about decades and hundreds of years. So time scales are way, way far apart. But billion years is something you can be worried about too. Yeah, if you can be around to have this a problem, you've done a good job. Yeah. Can you speak louder, please? Sorry. Yeah, there's a paper by a guy, well, Steve Benner has looked at this. He's a biochemist in Florida at an institute called Flames. But there's also a guy at MIT working with Sarah Seeger, who has in 2004, the National Academies of Science was trying to figure out, hey, what are the limits of life? And William Baines is his name, and he's probably the person who has looked into this most carefully. He's a biochemist who has paid a lot of money by the pharmaceuticals to find medicine, but he's also somebody who got interested in this issue of other liquids. And read his paper, I think it's 2005, Bill Baines in the journal Astrobiology. He's also, as I said, in Sarah Seeger's group, and they're leading the charge in terms of trying to figure out biosignature molecules. So when I would look at this problem of biosignature molecules, I would try to look at the metabolisms of critters we know about, and they're kind of, like for 4 billion years, Luca, what was the metabolism there? But the approach taken by Sarah Seeger and William Baines is, let's consider all possible molecules. They have like tens of thousands of molecules that they're looking at, and then they're going at them one by one to figure out which are the ones that are easiest to detect, not which are the ones that are most probable to be the result of life. So it's a different strategy.
For life from under the surface, for example, can gas giants have a water sea below?
Yeah, well, usually there are two things when you talk about alternative life, and that is getting life started and then maintaining life. And because we have life here at the surface, as I said yesterday, the bioshell is only about 10 kilometers thick. But that's only because as you go down deeper, it's a geothermal gradient of about 20 degrees per kilometer. So you go down in a South African mine to 2 kilometers, it's 40 degrees warmer than at the surface. So about 20 degrees is per kilometer. So life dies back then because we have an upper limit. Right now, the upper limit of life is about 122 Celsius. Well, I've never heard of a fluid layer, but Carl Sagan has speculated about there are regions in Jupiter's atmospheres that is warm enough to have clouds of water. And I don't know how deep that is, but he was putting bloated life floating around. One of the arguments I've heard against that idea is that here we have Earth, we have an atmosphere. There is life in the atmosphere, but it's usually bacteria that has been blown up there. Apparently there's no life that completes its life cycle in the clouds. And so, I don't know, maybe you need liquid water bigger than a cloud droplet to do that. Be free to speculate. Yeah.
What is the parameter that defines the habitability? Is it only the temperature?
Water has a triple point. The pressure on the surface of the planet, it's going to have water, has to be above the triple point. As I said, Mars does not have enough pressure to do that. It has lots of H2O, but it's either ice or vapor. No liquid water. We see evidence for liquid water in the past, therefore the pressure used to be above the triple point. So basically, it's not just being in the habitable zone, it has to be a planet that's massive enough to be able to hold on to an atmosphere thick enough to be above the triple point pressure of water. So a little bit, it's not, I mean, we were 1 bar, I think is it 6 millibar or something? Anyway, maybe it's about 10 millibar. So 1/100th of the atmospheric pressure that we have in this room is sufficient to get water above the triple point. So that's one thing. You have to have a massive enough planet and rocky, and to be wet, it has to have that atmosphere. The moon, for example. The moon is in the habitable zone of the sun, right? But it's so small it doesn't have an atmosphere. So therefore it can't have water, and it's all dried out anyway. But if it did have H2O, it still wouldn't be habitable because it would either be ice or vapor, and then it would just dissipate because the surface gravity is so small. So we're looking into these. We're looking into these planets because we know their masses and radii. We're getting the density because we know the density, and that tells us what the surface gravity is. The surface gravity tells us what kind of gases it can hold on to, given that we know how far it is away from the host star and what the effective temperature is. So all these are new parameters that we're putting together to see what kind of atmospheres you can have as a function of mass, radius, host star, etc. Yeah?
Have they considered magnetic fields, Charlie?
Yeah, have they considered magnetic fields? Yes, my student Sarah McIntyre had just wrote a paper on this. So the idea is, do you need magnetic fields to protect life? Now, the Earth has a magnetic field, and the Moon doesn't, Venus doesn't, and the idea is, the Sun is putting out these electrons and protons. Because we have a magnetic field around the Earth, the dipole, the particles come, hit the magnetic field lines, and spiral down. They come into the atmosphere, then they get funneled through the North and South Pole, and you see the Aurora Borealis, Aurora Australis, and, but it protects us from a large fraction particles coming from the sun. And so, but then you ask the question, okay, let's assume that you need a magnetic field to protect life. So what we did was figure out what were the probabilities of the exoplanets whose density and mass we knew, size we knew, and said, okay, does it probably have a magnetic field? The problem with this is we can't tell how fast the thing is spinning. And we think that spin is something that's necessary to produce a magnetic field. So what Sarah thought of is, let's just, these things, most of the things that I just said that we have the mass and the radius for are tidally locked because they're close into the host stars. So they're going like this, like the moon is tidally locked to the Earth, the same face. So their rotation period is the same as their orbital period, right? So their spin is the same as their, and so the question is that enough to produce a magnetic field? And we said, well, let's pretend it is. And so we did some calculations, and then we figured out which was the most Earth-like planet in terms of the probabilities of having a magnetic field that could protect life. That's the analysis that we did. Unfortunately, I'm not convinced that life needs a magnetic field to protect it for the same reason that we don't need an ozone field to protect us from UV. I mean, the great oxidation event happened 2.3 billion years ago. Before that, there's very little oxygen in the atmosphere. That means there was very little ozone. That means ozone, the UV could come through and hit the surface. But that's simple enough. You just get underneath a couple of centimeters of water and you're protected. Crawl under a rock, you're protected. So I think that these fears have been exaggerated, both in terms of ozone protecting us from UV, because life can figure out how to do that. All you do is make melanin, for example, or hide under a rock, or get under a little bit of water. So I don't think UV is an issue, therefore I don't think oxygen is an issue to protect it. Similarly, about magnetic fields, you know, here's a project that I want somebody to do. That is, the magnetic field of the Earth changes, switches. And we know by looking at the stripes on the other side of the spreading zones that when they've changed and what was their frequency, and also that there were times when there was no magnetic field of the Earth. So I thought, if it is true that a magnetic field protects life, then during the periods where the magnetic field was on its way to turn but it was very weak, you should see some type of extinction. And so you can correlate extinctions with the magnetic field reversal when it's low, and I haven't seen anybody do that. I've talked to a few experts about trying to do this. It's something it's an interesting project for a student to do, but it's something that we'll do in the next couple of years, I hope. And I'm guessing that the result will be there's no correlation that's significant between magnetic low periods and extinctions.
Even if there's no extinction, there should be some difference.
I don't know. It's not obvious to me.
Time scale.
It's not obvious to me that reducing a magnetic field, I mean, what do you think the effect would be? You think because you'd have charged particles hitting the Earth, therefore you'd have a higher rate of cosmic rays, therefore what? You'd have more DNA. Yeah, so during the reversal, what? During the reversal, you have a lower magnetic field? Or you... Well, see, if it doesn't matter whether it's north or south, so it's a reversal. If it's here, it's a dipole, it's doing the same thing to protect us. What doesn't protect us is when in between, when the dipole turns into something other than a dipole, the strength goes down, less protection, and then you get hit by more solar particles, that ions from the sun. And the question is, does that mutate DNA at a level that life can't deal with? And I say, hey, life has had to deal with it for 4 billion years. Maybe it's even useful. That would be my perspective. Well, what happens is that you have a dipole and it has some minor quadrupoles and some other octopoles. And what happens when you get rid of the dipole, the quadrupole gets a little stronger most of the time, and the higher order multipoles get a little stronger. So maybe the protection goes down a little bit. I'm not sure. But in other words, if you have a dipole, then you're radiating the north and south magnetic poles more, and here it gets protected. But if you have a quadrupole, then you have more places that it comes down. Higher order multipoles, it comes down in 10 different places. And I'm not convinced that that's an important feature to regulate the continuance of life on Earth. I think without a magnetic field, we probably could still deal with that. Yeah? Yes.
If there is a sunspot that we on the star,
Yes.
then it will result as simply.
Yes. Yes.
How exactly we can differentiate?
Right. That's one of the biggest systematic errors that they identified quickly, and luckily, now the sunspots you may know in the sun are about the size, some of them about the size of the Earth. And so they can easily simulate an Earth-like planet passing in front of a distant star. However, what they do is they find out if you look at the period distribution of the rotation of stars, you can see what that is. And it's something, I'm guessing 1 sigma, 10 days to, anybody know about solar rotations? I mean, young stars rotate faster because they're always slowing down because of magnetic braking. But to a star like the sun, I think the period's about a month or so. And so you have a sunspot that goes across in, let's say, half a month. And so that's very different from the several hours of the transits of stars that are further away. But they do, I mean, you could have one that's very close that's orbiting like that, but they reject things that are at the period of the spin of the stars, and they have estimates of, crude estimates of what's the rotation rate of the host star. But it is a major problem, and particularly the first 10 years of observations, that was a problem. Right now, the biggest problem is convection. You have convection cells, and they have cool spots and hot spots there as well. And so that keeps you from getting better than this velocity. So this is about 1 meter per second, and that's a lower limit that probably you can't get beneath because the surface is going like crazy at that speed. Yes?
Life that we have, or even the most primitive life, is it...
Oh, don't say use the word primitive with me, please.
Even if you consider the most primitive...
No, I don't believe in the word primitive, so go ahead.
I'm not saying we need to have very complex, but I'm just wondering if it is a function of, the mass. If you make Earth twice as massive as it was.
Yes.
You had a habitable zone there in the previous image.
Yes.
The habitable zone where the Earth had a very low mass. In that thing you put in the bottom place. There are other planets related in the habitable zone which have larger masses.
Yes.
How will the life that's formed there, even though there could be water formation, to the point, will the life that's formed there get affected by this mass?
Yeah, so you're asking what's the effect of mass, I think, on this plot here, right? So here's mass here. So this is in Earth masses. Here's Jupiter is right there, right? So these things in the habitable zone are gaseous planets. They do not have surfaces. And so most astrobiologists think that if you don't have a surface, you're not going to form life. Maybe you can, but most people think that's not the case. And so, as a matter of fact, right about here is the limit, right where rocky begins. Everything beneath about this line are rocky, and everything up here is gaseous, like Uranus and Neptune and Saturn and Jupiter. And so we don't consider them very habitable, but maybe they have habitable moons. If they're this big, they could have a moon almost the size of the Earth. Therefore, it could hold on to an atmosphere. Therefore, it could have water. So up here, you might have habitable moons around these planets. Here, they're so gaseous, they don't have surface. And here, and right here, and beneath is where we're looking for Earth-like analogs. And like I said, the radii of such things, of rocky planets, is about, the maximum is about 1.6 Earth radii, going down to about, 0.8 Earth radii. And that's the range we're looking in, because 0.8 is where you start to lose enough surface gravity so you can't hold your atmosphere, and 0.6 is where you turn from rocky into something else, either a water giant or a Jupiter or Saturn with so much gas that you have no surface.
There are no other questions? It's time for
All right. Thank you. Thank you. And thank you for inviting me.